Hi, thanks for the introduction, Shayna. Let me know if you can hear me and see the screen.
Yes, ma'am, we can.
All right, thank you very much. And thanks for joining the seminar workshop. I'll be talking about model interpretability today. And let's see. So the agenda today will start with the basics. What is interpretability and why do we need it? And then we'll talk about some of the dimensions of interpretability, like different types of interpretability methods and several things we should consider while we're doing model building. We'll then talk about several common methods. We'll focus on the model agnostic methods, and then we'll look at some examples, case studies. Feel free to ask me any question if you have any during the presentation. So let's begin. What is interpretability? So interpretability, or sometimes we also use the word explainability. They're kind of sometimes interchangeable, but sometimes people think one is bigger than the other. But in general, these are both pretty wide concepts. It refers to the ability for a human to understand a model. These days, more or less, we talk about machine learning models. Interpretability covers a wide range of applications and methods, but mostly we focus on explaining the model's behavior these days. So the specific method you use or the specific interpretations that you need are very model and context dependent. Usually people ask questions and then the researchers and the people who work on interpretability, like me, try to answer those questions with one method or the other. Questions include like, why is this individual's loan application got rejected? Why is the model predicting that the stock price is going down, or something like related to fairness and then transparency? Does the model make decisions using some information that we're not supposed to use? And sometimes that's harder to answer than just looking at the features or variables actually used, because sometimes even when you're excluding some information or features from a model, you can still leak the effect by having correlated features. So it's all of these questions interpretability try to answer. And we have developed different methods to deal with these problems. And we'll look at some of them. So why do we need interpretability? Why are people interested in answering these questions? Well, an easy example is because the models have become increasingly difficult to understand by themselves. Like linear regression is usually a good example of one of the easiest model to understand, but increasingly, especially in image processing, the model has becoming much more difficult to interpret or understand. For example, all the popular deep learning image recognition models these days, they easily have billions or millions of parameters listed here. Like even starting like year 2012, the parameters has gone to 62 millions and it just keeps increasing. So there's no way for a regular human being to look at the network, just look at those millions of numbers and understand what the overall logic behind the model is, or understand what it's trying to do, really. So you can look at the predictions, but if it makes a mistake, there's no way of knowing why. And it becomes harder and harder for us to control or give feedback to the model. And there are a few other concerns. For example, I talked a little bit about fairness and transparency. If you cannot understand a model, it will not induce consumer trust. And it will also does not help you to improve the model when you don't understand its inner workings. Also, sometimes like learning how it's working will help you understand something that's not obvious, and it might reflect some truths or facts about the mechanism behind the behavior. Also, there's like legal requirements for some of the models of, for example, the Equal Credit Opportunity Act, Fair Credit Reporting Act. They require that the financial agencies give reasons for why they were denied, why a consumer would be denied credit. So it's important that the companies are able to give reasons. That's all reasons why we need interpretability. So one question people sometimes ask is that why can't we just use simple models? Let's just, for those really, maybe not for all models, for some models, let's just use something simple like linear regression, decision trees, logistic regression, or rule lists. Why can't we just do that and be okay with it? So what's the big deal, right? So linear regression, for example, is easy to interpret most of the time. Basically, you can explain it by saying, look at the regression weights and say, hey, the weights means if my feature X increases by 1 unit, then the expected value of the prediction increases by beta, this feature weight. And linear regression can be generalized with link functions for classification tasks. So it's not just for numerical predictions. However, even for a model this easy to interpret, there are some questions sometimes not easy to answer. For example, if you add feature engineering, because linear model, you cannot model everything with a linear relationship. Sometimes you need to add a correlation, terms that x1, x2, or squared or something, or really more complex features to improve the model accuracy. And these kind of engineering makes it harder to explain because it introduces dependencies between the features. It becomes a little bit harder to say, hey, my increase of one variable only affects the model in a certain way, or if your features are correlated, excuse me, then it's also a little harder for us to understand. And other things like rule lists, logistic regressions, they're also easy when they're small. For example, for trees, when the depth is small, the number of variables is small, then it's easy to interpret. For example, this here, you can say, hey, if X is in a certain range, then the predicted Y is of this value. Or for a rule list, you can easily say if feature A and B exist, then the prediction Y of Y is something. However, if you increase the dimensionality and the depth, then this quickly make interpretations intractable. Even, for example, this. This is a decision tree trained on a data set with only 4 numeric variables. Actually, if you look at it, this decision tree only uses 3 of the 4 variables. And just by looking at it, can you tell what the overall decision logic is and what is the most important variable? You may say, okay, because the first split is looking at the petal length. If petal length is smaller than this 2.45, then the prediction class is setosa. If it's not, then we go down. So maybe the most important variable is this petal length. But for what about the other classes? For each individual data point, it might be that one of the other splits is more important for the decision. And how do you quantify give it a number of how much its importance is? It's also not very clear just by looking at this tree. And this is just using 3 variables. What about this tree? This is trained on a data set for predicting a disease outcome, and it's not even that big. The trees for example, in forests can easily go 100 levels. And those trees, if you look at it just with human eyes, is not very interpretable. So the quick story here is we call those like linear regressions, decision trees, and other open box models or interpretable models. They're great if they fit your need. If they are good enough for your accuracy, they offer some really reliable and well-defined explanations for some situations. But they may not answer all the interpretability questions you have. For example, the transparency, you might be able to inspect every feature weight, every variable that they're used, but it still doesn't tell you, is the model fair? Does it use maybe have like use features that's correlated with things that I don't want it to be? And also high dimensionality, increased complexity, or if you want to ensemble some model in any kind of pre and post processing, can add complexity to interpretations. So what do we want to really solve here? Obviously, the goal is not to inspect all the parameters of a model, because doing so does not really help us understand the model from a high level, from the human perspective. I like this quote by Kim in 2017 in her talk about interpretability. She says that interpretability is about knowing enough for your downstream tasks. So it's not that important sometimes not to know all the parameters, but maybe you want to know some high level informations. For example, for this decision, what's the most important features? Or what will happen if I change one value in this observation? Will the prediction change? And what features does the model use or does not use for the predictions? If I have several groups that I care about fairness among the groups, is there a difference in the decision-making process? So these questions can be answered with different methods, and there are specific methods targeted to each one of them. And we're going to look at some of the use cases where interpretability will help with these things. So these use cases, most of them are either a use case I've worked on or I've discussed with a customer of SaaS. And I cannot share the detailed model, but I'll talk about how it was used. Let's see. So this is, for example, the most common use case, legal requirement, where the financial institutes are required to give reasons when they deny credit. So the interpretations are needed for each one prediction to list the most important features that negatively affect the decision. And here we use a method called Shapley values, we'll talk about it a little bit later. Basically breaks down the decision by the individual feature importance. And by ranking it, you can give the consumer a breakdown of what feature was used in the decision and what impacted the decision most. Another example is for fairness and debugging. This use case we'll also see in the demo later. Basically, there is a model built for student admission analysis, and it predicts the admission probability based on student information, including features like SAT score, classes taken, and some extracurriculum activities. When we interpreted this model, however, we found that the prediction of students by county has a discrepancy between them. So basically, one county student has lower admission rate with even the same SAT score. And after investigation, we found out the reason was able to correct this unwanted discrepancy in the model. There's another example I took from a talk by Art Oven this year. This is basically he used the Shapley cohorts to try to understand the Compass risk scores. This is a pretty classic data set people use for fairness, transparency in model machine learning. Basically, this is a commercial model built to predict re-offense probability. So it's used to guide the decision of whether to let the to offer alternative sanctions for the people who is going to be prisoned. And the analysis show that there is actually a race effect in the model. Basically, the impact of race is if you're white, then your predicted chance is reduced because of your race. And if you're people of color, your predicted chance is increased. And that impact in the prediction is larger than the ground truth. So that reveals the model is potentially biased. Also, there's another use case by one of the customers. Basically, they model a potential failure in their warehouse by detecting salient system responses and conditions. And whenever they detect a salient point, that's a potential warning for a problem in the warehouse. However, it's unclear sometimes why there is a salient point. So they use interpretations to review the triggers and causes of the salient point. By having that, then the warning can be either dismissed if they know the cause of that point or investigated upon. We can also use interpretability for learning and understanding. Another use case is in crop selection, where the model predicts the crop yield based on location, weather patterns, and planting method and other information. The interpretations of the predictions help review what features are most important for success for a specific crop or a specific location. So when they're selecting crops for that location in the future, they can use this information to help guide the crop breeding program. Another similar case is when people are trying to build heat-resistant proteins. The model will predict a heat resistance of a specific protein configuration. And by interpreting this model, it helps the researcher find specific combinations of the amino acids or structures that contribute to desired heat resistance. And that helps them understanding better of their the protein. And there are many more cases. I think basically, whenever you're using a complex model, there's room for understanding, debugging, or transparency in the model that you can potentially use interpretability methods. So now we can talk about the dimensions of interpretability. So there are a few aspects of interpretability we might think about. Although most of the methods that these days we develop are focused on interpreting the models, there are actually more to the interpretability than just those methods. For example, even before you start modeling, as a data scientist, we all know we need to explore our data, understand our data. That is part of the interpretability. By exploring the data and understanding it, it will help us understand our model better in the future. During the modeling, we could construct more interpretable models, whether by using open box models like we mentioned, regressions, rule lists, and trees, or by adding constraints like monotonicity and fairness constraints, or encourage sparsity in features using feature selection. because when you use fewer variables in your model, you're going to have an easier time to rule out what is affecting the result. And after modeling, we can also use these post-modeling interpretability methods to help us understand further why a specific prediction is done, or how the overall model behavior is. There are usually model-specific and model-agnostic methods. Model-specific methods are built for specific machine learning models. Usually they explain only one class or one type of models. They can use model-specific information. There are a lot of model-specific interpretability methods specifically in deep learning, where they look at the network structure, or they look at the feature heat map to try to understand what features were extracted in the model in different layers and how they're used. There are also model agnostic methods, which they will work with most machine learning models, including deep learning. They treat models as closed box. So they pretend they're not, sorry, it's not a pretend. They don't know the inner workings of the model. Most of them rely on input and output analysis. Basically, you just change the input, try a bunch of them, and see how the model behaves. And by controlling your input and seeing the output, you can analyze what the model is doing. Those are specifically good for pipeline building when you may want to try out different models. Like, I want to try 10 different classes of models, and maybe one of them is good for this task, or several of them are good for the task, but I want to have interpretations on them before I decide on which model to use. Then model agnostic methods allow you to apply the same interpretations to all these models without having to change the interpretability methods every time you try a different model. There are also global versus local explanations. Usually global explanations explain the overall behavior of the model. For example, the global feature importance or the partial dependence we'll talk about a little bit later. It tells you the overall trend of a model. And local explanations focus either on a specific region in the model or focus on one single prediction or decision. And examples include Lime, ICE, and Shapley values. We'll talk about all of these later. So, any questions up until this point? Okay. I think we're good. So we'll move on to the interpretability methods. These slides about the specific method I borrowed from one of my colleagues, Ricky Tharrington, who also gave some talks about interpretability in previous workshops at NC State. I think you can find, I posted a link here, and if you want to look at some of the more detailed descriptions or explanations of these specific methods, feel free to go take a look at his presentation. So here we use some synthetic data. We generated some synthetic data and and generate some Y label, which we add a certain amount of noise. So the X1 is a linear relationship. Then we have a sinusoid relationship with X2, then parabolic relationship with X3, and X4 is the absolute value. So these, you can see the data is relatively noisy. And we use a GAM model to predict the outcome. GAM does a very good job at predicting these synthetic data. And one thing to note that because the model is additive and GAM is also additive, there's no like interplay between the between the variables just for simplicity. So the first method we'll talk about is individual conditional expectation. So all the methods I'm talking about these today are common model agnostic methods that are very popular. And because they're model agnostic, they can be applied to almost any model that make predictions or decisions. To compute ICE, you basically pick a single observation and pick a single variable. Then you change that variable, keep everything else the same, and move that variable within the range that's observed in the data, and score the model with all these different values and plot. And then you can repeat for other observations to compute the ICE for them as well. For example, here, we just pick x3 as the variable, and we pick that dot, which is our observation, and we change the value of x3 of that observation and just plot out a curve of what the model would predict if the x3 is changed to the other values. And this can be repeated for all the other observations. The individual ICE is a relatively simple method. So one easy question is, once we have all these curves for different observations, these are all for each individual decision. What about the average train? As you can see here, this reflects the parabolic curve of the model pretty well. So the natural extension is partial dependence, which evaluates the model's prediction on the variable on average. So it's simply the average of all the ICE of all the observations in your data set. Partial dependence answers questions like, how does the model's average prediction change for different values, instead of how does the model's prediction change for this one single observation. You can also consider interactions by calculating multivariate PD. And in this specific case, there's no feature correlation, but if that's of concern, there are some methods that specifically consider this. For example, accumulated local effect, ALE, is an extension of a PD and also can be used. So to compute the partial dependence, we just compute the ICE of all observations, and then we average it. On the right here is the average of all the ICE curves for this data set at x3. And that shows us the general trend of the model that changes with the change of x3. We can do that for all the variables, x1, x2, x3, and x4. As you can see, the partial dependence plot shows reflects the original model pretty well. The only one that's slightly not as obvious is x4, which is absolute value, but it seems a little bit curved at round like 0, which is because we only take like discrete points of x4. If we take more points, it will look sharper. But we didn't do that because that's a little bit of cheating. So any questions so far about ICE and PD? Okay. So once we move, so PD is a global variable trend interpretation. LIME is a local interpretation method. LIME has become pretty popular because it's pretty fast to compute and gives you local analysis of the model. What it does is it builds a local surrogate model and helps you understand the local behavior of the model. So what it does is it picks a point. So to compute Lime, you pick a point in your data set, any point that you want to explain around, and you generate data around this around the point of interest, and then you train a linear model on those data you just generated, and you inspect the coefficients of that linear model to see how the model behaves locally. So if we look at some visualization, this is just a partial dependence plot of the model we've seen before. And we pick a point. It takes the x1, x2, x3, x4 values of these at the dot. And then we'll generate a bunch of random points based on the distribution of the data set. So all of these methods are data dependent because we need to understand the distribution of the data, right? In order to explain anything. So you generate these data and you fit a linear model. And it tells you the local trend near your point, how the decision boundaries are defined. So you can see it almost looks like it's taking a tangent line to the PD curve near the location of the point you chose. So it shows us, for example, x1, if you increase it locally, then your y prediction will increase, which is correct according to the model. And all the others is the same way. For example, x4, you can see the PD curve, the global trend of the model is going down when x4 is smaller than 0. And here we see the local trend near this point, which is smaller than 0, is also the y hat is going down if you increase the x4. Lime, there are a few issues with it. It's a linear circuit model, which basically you're reducing a complex model to a easier to interpret model at a certain location. However, because it is local and the data generated is also local, there raises a question about what counts as local. Exactly how big the region should I consider? For example, in here where x2 changes, it's the relationship between y hat and x2 changes direction when the x2 is different. If you take x2 as -2 or -1, the trend of the prediction is different. So if your local includes too big a region, you risk of averaging different trends. And if it's too small, then you might have some data generating issues. And also, similarly, how heavy do we weight the close by samples, and how many features do we select with lasso? So it's useful to understand the local trends of the model, but there are some tuning issues that need to be careful about. But one thing I want to point out is some people would use Lime to tell you that the feature coefficients are the importance of that feature, which is, in my opinion, not correct, because it tells you the local model trends, but not the individual feature importance. Just because the model moves quickly in that region with this variable does not mean it contributed like significantly to the prediction. For individual feature importance, actually, I recommend Shapley values. They're usually a much better fit, and we'll talk about it next. So Shapley values come from the game theory. It solves a problem of reward distribution among multiple team members. This was originally solved in 1953 by Shapley, hence the name. Basically, the question is, say we have 3 team members, A, B, and C. They worked together and earned a reward of total 15,000. And how do we fairly split the money among the 3? There are many ways you can do it. You can say, oh, everybody gets the equal amount, but what if one contributed more than the other? So this becomes a mathematical problem. Basically, how do we fairly attribute their contribution? There are several things we should consider. I think these are pretty good constraints. Efficacy, for example, all the individual rewards should add up to the total earning. So A, B, C, three people totally earned 15K. So all the individual rewards should also add to 15K. Otherwise, if you don't add up to the number, how do you deal with the leftover or deficit? The dummy assumption, if including an individual X brings no additional earning in any situation, then that individual should receive 0 reward. That should be pretty obvious too. Here we say ABC earned together 15K, but if we say have a person D that they come in sometimes, just look around, but it doesn't improve their earnings at all, having that person in does not contribute to more earnings, then that person should not get any reward. Symmetry. If two individuals add the same amount in all situations, then they should receive the same award. Then the last one is additivity. If including one individual increases the earning by the same amount of two other individuals, then this individual should receive the sum of the other two just because they bring in more value. So it turns out if you apply all of these 4 constraints, there's only one unique solution to this problem. What you need to do is to look at the earnings of all the combinations of the team players. Say having none of them, what's your earning? Have just one person, what's the earning? Have two, and have all three, what's the earning? And then you calculate the additional value the individual brings in by including it minus by not including it. For example, here, not having anyone is earning is 0 and including A gives you 4K. So in this situation, A's improves the earning by 4K. But if we have adding A to the team B, having A and B improves the earning by 9K minus 4K equals 5K. So those are all the different situations, how much that person could improve the earning, and we average them with some weights, and then we can satisfy all the constraints and calculate the individual contributions of that person. So for this specific example, it turns out that A contributed on average 4.5K, B 5K, and C 5.5K. And that adds up to 15K, and that's how we should distribute the earnings to the 3 people. So obviously this calculates the contribution of a team member, and it satisfies all the nice constraints that we would like. So naturally, we would want to extend this to compute feature importance, and it has been done. And what we do is we evaluate the model's predictions with different combinations of feature values. And by comparing them with not including that feature or having the feature with a different value, we can compute the importance of that feature. So imagine A, B, C are not people, but they're really variables. Then having that variable or not having that variable will give you different predictions. Then you can calculate the importance of that feature. This answers individual feature important questions like what feature contributed most to my current credit score and how much did it contribute? This, however, if we do it in the original method, is very computationally expensive. So there are a lot of approximation methods which are much faster. There's even one tree-specific method that is very fast. And if you have any problems that you need to assess the individual feature importance for a specific prediction, I recommend using Shapley values. This is just an example of taking an observation and look at the Shapley value where we just plot out as the red line. And it turns out for the specific model, which is not true for all models, but for this additive GAN model, the Shapley value is simply the intersection of this X value and their PD curves. All right, we are a little bit tight on time, so let's move on to the case studies. Can you see my screen on the HTML file?
Yep.
Okay, great. So we'll look at two examples. The first example is a brain tumor, a tumor detection. Basically, this is looking at the, sorry, this is not brain, but some lesions in the body. So one team in SAS developed a model to look at the pictures of body CT scans and predict where the lesions are. And it will label out individual lesions and give them probabilities. So all of these methods require that we set a threshold on the probability to detect make the final decision. So the problem is, this is in this image labeled by a clinician, the ground truth labeled 5 lesions. But if you set a high threshold, then it's easy to miss out some of the not as obvious lesions by the system. Or if you use a very low threshold, then you have many false positives. And these are all problematic because we do not want to miss any actual lesions, and we do not want to have a lot of false positives. These pictures, after labeling by the machine, will be sent to review by the clinicians. If you have just false positives everywhere, then it's not useful for them. So what we wanted to do is to create a system where we can separate these cases where we have high confidence by the model saying, see, these two, there are 2 boxes that always show up in all the threshold situations, and there are some that show up only when we lower the threshold. So we call those that only show up when we lower the threshold the marginal cases. Basically, the model is not 100% sure whether that's a lesion or not, but there are some characteristics in the image that made the model think it potentially could be a lesion. And usually you can see for the high confidence detections, there's a defined border and the color is darker. And for the marginal cases, actually all of these I showed here are actual lesions, but some of them are really, even for my eyes, which is untrained, is pretty difficult to tell if it's a lesion or not. Obviously, if you hand it to a clinician, they'll have a better idea, but it's not always obvious. So we want to separate the cases where the model would predict with high confidence and low confidence. And when we have a marginal case, what we do is we compute the Shapley values. Remember, Shapley values give you the individual feature importance of a single decision. So in this case, each bounding box has a little patch of image, and we'll make a prediction on that patch, whether it's a lesion or not. And if we calculate the Shapley values and color code it, overlap it with the lesion image, we can show what pixels contributed positively or negatively to the prediction. Here in the explanations, the red or the redder color says these pixels made the model think this is potentially a lesion. And the green colors show that these are the pixels that made the model think this may not be a lesion. And by having the side-by-side image, the clinician can have a better idea of which region to focus on to analysis, and it gives them a faster turnaround to decide if that should be a lesion or not. Then they can click yes or no, reject, or accepted as a lesion. So this is one example where we could use individual feature importance to help make the clinician diagnosis process faster. The other example we talked a little bit about is the school admission example. So here, the model is trying to predict the admission probability given some of the student features. For example, SAT scores, math class taken, GPA, some extracurriculum activity, and their high school ranking. So this, first of all, what we did was to plot the partial dependence for each of the individual features used in the model and see how the model in general predicts based on these features. So it's clear that the SAT score and the highest math class they've taken specifically for this college, they significantly increase the predicted probability. And the other three features are not used as much. The high school ranking specifically does not affect the outcome at all, which looks reasonable. But is there a difference between between the counties? What we want to understand is whether the model is predicting fairly among two different counties. So then we plotted out the individual ICE curves for different students in County A and County B. County A colored with this teal color and County B this orange color. And we see that there's a trend if we plot the average of the ICE curves by county, then County A students seems to have a higher probability of admission for the same SAT score compared to County B students. So this raised a question of why this is the case. I mean, you don't always want to balance them out, but if there's an actual cause between this discrepancy, you may want to address it in the model. So go back to data exploration to discover the actual cost. What we did was to plot out the normalized mean difference, basically the difference between County A and County B in terms of their features. So it turns out for the students of two counties, their SAT scores, GPA, and extracurriculum activities have relatively similar levels, but the highest math class number for County A is significantly higher than County B. If you plot out the percentage of the students taking different levels of math classes in these two counties, it's obvious that County A offers higher level math classes more than County B. And this is not a fault of the students necessarily, but really a problem with the courses it offer. So after revealing this discrepancy, the modeler decided that we want to correct it by balancing the data specifically in the math class level by county. After balancing, you could see on the left column, this is the original ICE curves and the original average of the prediction probability. On the right is after you balance the data of that specific feature, the County A and County B students' probability of admission no longer separates, and their predicted probability of admission are almost the same when they have the same SAT score. That would conclude my presentation today. And is there any questions?
I notice you have one question in the chat here from Grant Fleming. Have you found any practical differences in using sets of ICE plots versus a single PDP plot to communicate global feature effects? An image of a ton of ice plots can be hard to read, but it does provide a more precise picture of the overall uncertainty around your global feature impacts.
Thank you. That's a great question. And actually, I think this plot shows you right here is a good example. So individual ice plots, yes, it shows more of a trend of, and you can see the distribution of the ice plots of the predicted values. And actually, in most cases, I think it's good to have both. So PD plots give you the global trend on average, and ice plot give you the distribution of these individuals. So if you have both, you would be able to look at the trend and how they distribute. Is it like really tight around the average, or are they really dispersed? Are there, you can, with grouped like ice plots, you can even see, are there group differences? And those give you a more complete view of the problem. I hope that answers your question.
Yeah, that's great. And then also, what's going on in the balance data with county A and B with the sharp downward angle we see in some curves?
Oh, there is okay. So that's an interesting effect. So the balance data, uh, really, this is probably an artifact of that model. And that's a good observation. Actually, this is not the final model they used to for this specific decision, but this is more like a prototype. So usually this kind of effect is not desirable. What we would do to correct it, if you see a trend like this is a very good observation. We would want to apply some monotonicity constraints to the model to make sure that a student having higher SAT score would not be penalized.
Great. And another one is, does SHAP work for a rule-based model?
Does SHAP work for a rule-based model? The answer is yes. You can still compute the, but the problem really is you, in order to compute the Shapley value, you need the a numeric prediction. So for most of the rule-based models, if you can compute a predicted probability, like the trees, then you can do it. If you don't have a predicted probability, then it's harder to compute the Shapley values. You can still compute it by saying, okay, if the target, I can say if I predict a positive outcome, then I can say that's 1. If I predict a negative outcome, then the prediction is 0. Then you can still compute the Shapley values, though it's usually better if you have a more continuous prediction.
Great. One more from Brian Shalloway. I imagine that Shapley values take a long time to calculate, as you have to build models across all combinations of features. Do you recommend ways for how to handle when you have lots of features? For example, a technique for an approximation of Shapley values?
That's a great question. So yes. So the original Shapley method would require us to train a lot of models based on different features. This is usually very infeasible because of how long it takes. So people have reduced that to not retraining the model 2 to the m times, but rather we just look at the predictions of having the variable to be of a certain value or not that value. Say you take it to be if you have a point of interest, so you look at the model, taking the value of all the combinations of that variable with that specific value taken from that observation, or it take other values. So it reduced to averaging a good number of expectations, but not retraining the models 2 to the m times. So that alone save us a ton of time. But still, even with that, there's 2 to the m combinations, and it's still time consuming. So the most common approximation methods we have, for example, SHAP, which has an open source package. They use kernel SHAP. SAS also has that. There is also a SAS specific implementation of Shapley value approximations. It's called HyperShap. That's a very fast and accurate Shapley value approximation method. And I recommend you checking it out if you have access to it. There's also another one. If you're using tree models specifically, there is a method called TreeShap. TreeShap is model specific, so it only works for tree models, but it calculates the actual Shapley values with the expectations, not the model retraining, but it calculates the actual Shapley values there, and it's very fast.
Thank you. There's one more in the chat. How do you balance the data when the higher level classes never occur in one of the counties?
So there are several ways you can do it. Basically, this specific case required us to normalize this specific feature by county. So basically you say, because the students in county B never took classes 7 to 9, we have to manually reduce. You can either cap, say, okay, for county A students, if you take level 6, or higher, we'll all take you as level 6. But that also changes the distribution, inflate the distribution of county A at level 6 classes. So you can curve, basically doing almost like a GPA curve. You curve their distribution a little bit and make the two distributions similar to each other. So a student in county B taking level 5 or 6 classes is treated the same as if they're taking level 8 or 9 classes in county A. I mean, this is not always desirable, and sometimes this practice could be even not acceptable. So all of these processing or fairness is a thorny issue in many cases, and they're highly case dependent. So you really need to be very careful about what is acceptable or what is not acceptable, right?
Yeah, it's a great illustration of the art that is data science.
Right.
I think this is a really great example. One more from Eric Guzman. Great talk. What are your thoughts regarding explanations quality? Considering we have many methods and possibly different results, how would you evaluate the quality of each explanation to select the best one?
Okay, that's a very good question. Thank you for asking it. I did not have time to compare all the methods today, but as you can see, most of the methods, especially the model agnostic ones, rely on some simple analysis of input outputs. So they have a very, very clear mathematical explanation, but there are problems with each of them. For example, PD, ICE, they do not deal with feature correlation in the model. If your model has feature interactions in there, I mean, PD can plot feature interaction. Sorry, that's not what I meant. PD can plot feature interactions if you have multi-way PD, but when it's generating the data, it separates the data and does not consider feature correlations. So if you have correlated data, then you will also often see that in certain regions of PD, it might seem like it's not as sharp, or the trend does not look as good. It sometimes is because of this broken correlation. And a lot of these data generations can create unrealistic data. For example, you could have features like age and years of education. And if you generate new data, you could easily generate a 7-year-old who has 20 years of education history, which is not natural or possible. And that creates other problems. So I think in terms of selecting a method, it's important to know first know your data and know your model. So if your data has a lot of feature correlations, like PD has a specific alternative called ALE that helps address this issue. Shapley values also has new methods called the Shapley cohort by Oven. It's a very new method, just came out a few years ago, that also addresses these kind of unrealistic data generation. So I think it's important to understand on a case-by-case basis what kind of data and model you're dealing with. Also, it's important to understand what the method can or cannot do and what it really is saying. For example, a lot of people would use Lime for feature importance, which is not the best thing to do, and I would recommend Shapley for that. But if you want to understand the local trends, Lime is a good method to use.
Thank you. Are there any other questions for Dr. Hunt? Well, thank you so much for joining us. We really enjoyed the talk. I love the examples you brought, especially, some of the things that you might not think about with model interpretability being used within the model building process. We have a 15-minute break where you can grab some lunch and come back and watch the book buffet moderated by Elena Snavely from SAS. So I hope
Thank you so much for having me.
Thank you.
All right, bye.